Hi, my name is Shenkai Wu. I'm a fourth-year PhD student in the Northwestern University. I would like to present our paper, SuperPack, Dishonest Majority MPC with Constant Online Communication. This is a joint work with Daniel, Vipo, Antigone, and Ivan. Secure multi-party computation, or MPC, is a cryptographic protocol. It allows a set of M parties P1 to Pn to securely compute function defined as f, which takes input x1 to xn from these M parties and output y. And the security requires that no information is revealed during this computation except for the output of the circuit. We designed an MPC protocol in the following settings. We assume M parties P1 to Pn, and this function f is represented by an arithmetic circuit with addition gates and multiplication gates. We assume dishonest majority. Specifically, we define a constant epsilon, which lies between 0 and 1/2. Our protocol can tolerate at most t equals to n multiplied with 1 minus epsilon corrupted parties. So this epsilon is the percentage of the honest parties among these M parties. And we assume a fully malicious adversary who can control at most T parties, and our work is actively secure. For our work, we design a MPC protocol with constant online communication per multiplication gate among all parties. We can tolerate any number of corruptions while this epsilon is lying between 0 and 1/2. And the communication of our protocol decreases as the number of the honest parties increase. We leave the specific communication overhead for the three phases of our protocol: the online, the circuit-dependent preprocessing, and the circuit-independent preprocessing. From these numbers, we can see that the communication is indeed decreasing as the increase of epsilon, which is percentage of the honest parties. We compare with some previous works that in the similar settings. The first category is the Spitz family. These protocols assume all but one corruptions, which means it tolerates n-1 corrupted parties. But it is not clear how this protocol can benefit with the case when there are more than one honest parties. Probably the best method is to remove a subset of n-t-1 parties and let the rest of t+1 parties to carry out the result. Another work is the GPS22. It achieves 58 over epsilon plus 96 over epsilon squared total communication per multiplication gate. Similar to us, its communication cost benefits from the increase of the honest parties, but the cost comes with large constants. There's another line of work on multi-party gobbling protocol, like tiny keys, and they work for Boolean circuits only. And they also consider n multiplied with 1 minus epsilon corruption, but they focus on reducing the gobbled label size during the preprocessing phase. And the last is the SuperPack, which is the honest majority MPC protocol with constant online communication. This is also a starting point of our protocol, but it only works for honest majority setting. We compare with a previous concretely efficient work called TurboSpeed. Here, n is the number of parties and epsilon is the percentage of honest parties. Both protocols, communication cost divided by three phases are shown in this table. And both the online phase and circuit-dependent preprocessing phase of the TurboSpeed protocol have communication cost linear to the number of parties, and this is the main difference between these two protocols. Here, we assume that the preprocessing phase of the TurboSpeed is instantiated by the method from Le Mans, where they realize the functionalities of VLE and OLE from the surrounding correlation generator, which achieves the sublinear communication. So this part of the cost is not reflected in this table. We compare with the online phase of the turbo speeds in terms of these two parameters n and epsilon. We study at which point our work would outperform the turbo speeds in terms of the online communication cost. And our work generally would benefit with larger number of parties and a larger percentage of honest parties. From the left, we fixed several epsilons and study the minimum number of parties we need to outperform turbo speeds. When epsilon equals 0.1, the SuperPack needs at least 34 parties to outperform it. When we increase the epsilon to 0.2, the n is decreased to 19. When we further increase the epsilon to 0.3, we only need a minimum n of 15. And we also fix the n's and study the percentage of honest parties we need. When n equals to 2 to the 5, the epsilon will need to be at minimum of 0.26. When n is increased to 2 to the 6, the epsilon only need to be 12% for the SuperPack to outperform turbo speeds. And when n is increased to 2 to the 7, we only need epsilon to be larger than 66%. And we also compare with turbo speeds in terms of the pre-processing phase. And this is the communication cost of pre-processing for both protocols with different choice of n and epsilon. And generally, the SuperPack has advantage for small epsilon and a large n during the pre-processing. And the ratio of the turbo speeds over SuperPack is between 0.83 and 1.6. This means that the SuperPack does not always achieve advantage over the turbo speeds in terms of the pre-processing communication. But we argue that the cost is reasonable considering the performance gain we get during the online phase. We implemented the online phase of both SuperPack and turbo speed, and we compared the running time factor of turbo speeds over SuperPack. At the bottom, we listed the communication ratio of turbo speeds and the SuperPack with varied number of parties and the percentage of honest parties. This will serve as a baseline of our comparison. When under the high bandwidth network, the computation is the bottleneck. And in this case, the SuperPack's advantage on communication is not reflected on the runtime. And also the SuperPack has larger communication overhead. Also, the SuperPack has larger computation overhead because of the use of package messages. But our implementation is pretty rudimentary, and it can be further improved with more advanced algorithms like FFT. Under the low bandwidth network, the communication becomes the bottleneck. And in this way, the comparison of the performance aligns with our analysis of the communication factor because the performance is restricted by the overhead on the communication, and the SuperPack does have the advantage on the communication overhead. We also implemented the pre-processing phase of the SuperPack, except for the calls to the functionalities like VLE and OLE during the circuit-independent pre-processing. Here we assume a trusted dealer distributes these values. And for these functionalities, there already exist the methods based on the surrounding correlation generators, which would achieve sublinear communication. And we show the running time of the SuperPack across 3 phases when the percentage of honest parties increased from 30% to 40%. In these benchmarks, we use the circuit size with 1 million gates, and we assume that n equals to 48. And as you can see, the Both the online phase and the circuit-dependent preprocessing phase are super efficient in terms of the running time, and the independent is slower, but the cost is reasonable. Next, let's delve into the SuperPack protocol, and I would like to introduce the background on packet sharing sharing. First, define three parameters N, K, and D, where N is the number of parties, K is the packing parameter, indicating how many secrets will be packed in one share, and also the D is the degree for the shares. The packet secret sharing is denoted as a vector V in a bracket with a subscript D, and the V is the input secret vector. We first define K plus N distinct values, alpha 1 to alpha K and beta 1 to beta N. These are the evaluation points. And next, we define a degree D polynomial satisfies f alpha I equals to Vi for I in range from 1 to K. This means that these V's will be evaluated at these K points. And we also randomly sample another D minus K plus 1 points. These D plus 1 point evaluations would determine this polynomial F with degree D. At last, each party PI will learn the value of F beta I as their shares. Our protocol keeps mean invariant for each Y indexed by alpha, with each Y value V alpha, which is the field element. We'll sample a random lambda alpha, which is another field element, and define its value mu alpha equals to V alpha minus lambda alpha. Obviously, mu alpha and the lambda alpha determines the value of V alpha. So in our MPC protocol, parties never explicitly share the value of V alpha. Instead, they simply share the value of lambda alpha and let the P1 as the king party know this value of mu alpha. And originally, the packet sharing is mainly used for the computation of SIMD circuits, where the same circuit will be evaluated for multiple times in parallel. There have been some previous work studying how to utilize the packet sharing and make it work for arbitrary circuits, including the previous work of GPS22 and the SuperPack mentioned earlier. And in our work, we also enabled our MPC protocol based on the packet sharing and make it work for arbitrary circuit. And the main problem is that the K wires in each packet share may come from different packet shares from the previous layers, as shown in this figure. As you can see from this figure, during the computation of the multiplication gates in layer I, we'll need the packet shares of this V6, where the values in vector V6 come from the values of the previous layers, but these values are packed in different shares. We need a mechanism to make sure that these values from the previous layers are correctly extracted and arranged to be the same share, to be the new share V6. And for example, for the batched gate input wire alpha, which are the input wires of a batch of multiplication gates in layer I, we'll need the shares for mu alpha and lambda alpha. They are all from different packet shares of the previous layers. And we follow the framework of SuperPack to maintain the wearing consistency and our invariant. Specifically, during the circuit-dependent preprocessing, parties will prepare the shares of lambda alpha for each individual wire alpha. Then the parties will construct these packed shares of lambda alpha with K shares from these individual shares. And at this part, the communication cost mainly comes from the degree reduction, because the parties are able to arrange the shares of this lambda alpha with degree m-1, but if the parties need the shares of vector lambda alpha with lower degrees, they have to do a degree reduction. And during the online phase, for any batch of k wires alpha, whose wire values has already been computed, as mentioned earlier, the P1 as the king party knows all the values of mu alpha. So it will locally arrange the correct mu alpha with no extra cost during the online phase. And this mu alpha does not reveal any information about the circuit Y values as long as the lambdas are secretly shared. Here I would like to introduce a simplified version of our online protocol. Here we assume that there is a batch of k multiplication gates. Gate inputs are defined as the vector v alpha and v beta, and they are determined by the mu alpha, mu beta, and the lambda alpha, lambda beta. And the output for the gate output, and parties already know the shares of lambda gamma, and the task is to compute the shares of mu gamma and reveal the values to P1. And at this point, P1 knows mu alpha and mu beta from the previous gates. And the P1 will secretly share these values as degree k-1 shares. Parties also obtain the shares of lambda alpha, lambda beta, lambda gamma, and this Captain gamma gamma, which is associated with the element-wise multiplications of lambda alpha and lambda beta, minus lambda gamma. And all these values will be obtained from the preprocessing. Using these values, parties will compute the shares of mu gamma in the following ways. When they get this degree m-1 shares of mu gamma, they will reveal the values to P1, who will reconstruct the mu gamma and use it for the gates in the next layers. The previous description of the protocol is a simplified version. Here, for this value of capital gamma gamma, we have an element-wise product of lambda alpha and lambda beta. And during the circuit-dependent preprocessing, this value and this product will be computed by a packed beaver triple. And in our actual online phase of SuperPack, we'll actually combine the computation of this product of lambda alpha and lambda beta via this packed beaver triple and the computation of mu gamma together. This would help reduce the computational overhead, including both the number of field elements sent between these parties and also the round-trip communication. Because if we do them separately as indicated by our simplified version, each of these steps will incur the communication overhead and also the round-trip communication. So our actual online protocol goes like this. During the preprocessing phase, the parties will obtain the shares of lambda alpha, lambda beta, and lambda gamma. They'll also obtain a packed beaver triple ABC. And during the circuit-dependent preprocessing, they'll manage to have P1 to compute the values of V alpha minus A and V beta minus B. P1 will distribute these values as the packed music shares with degree k-1. Using these values, it's enough for parties to compute the shares of mu gamma in this way. And at last, parties will reveal the shares of mu gamma to P1, who will reconstruct this vector. And next, I would like to introduce how we achieve active security. Our idea is to use the message authentication codes as the previous dishonest majority MPC protocols. we introduced two new notations. The first is the Shamir-seeker sharing, where the value is shared at one point alpha I, and we indicate this index I in this notation. And also another is the additive share. And we assume that the parties will secretly share this global key delta, which is the field element, and it will be shared in the form of Shamir-seeker shares evaluated at k different points. During the circuit evaluation, the parties will not only obtain the seeker shares of these values, they are also obtaining the additive shares of the authenticated version of these values, as shown in this figure. There are different ways to obtain authenticated shares. And the first is to directly get authenticated additive shares from the VLE. This is the same case as the previous protocol on dishonest majority MPC with additive shares, like the speeds. And the second is the random authenticated packed Shamir shares from the VLE. This is done by first obtaining the authenticated shares in additive share version via the VLE protocol, and then locally convert to packed shares, where the secret is random. And the packed share is of degree n-1. If the parties need the packed Shamir shares with lower degrees, they'll have to do a degree reduction. And the third is to get authenticated additive shares from authenticated packed Shamir shares. This is done by first obtaining the authenticated packed shares of the secret vector V, and then locally converts them into additive shares of the authenticated version. Now let me introduce how to compute authenticated values during the online phase. And this description aligns with our simplified description of the online protocol in the previous slides. And the first P1 knows value of mu alpha and mu beta, and they are reconstructed from during the computation of the previous gates. Then P1 will distribute these values to all other parties in the form of the packed Shamir sharing with degree k-1. During the pre-processing phase, parties also obtain some authenticated values, like the authenticated lambda alpha, authenticated lambda beta, and the authenticated capital gamma gamma, which is the product of lambda alpha I and lambda beta I minus lambda gamma I. And these are only additive shares, but not packed shares. The computation of the authenticated values during the online phase does not introduce any extra communication overhead. And we do it in the following way to compute this authenticated mu gamma I, where this I ranges from 1 to k. And the first term is obtained from the packed shares computed during the online phase. The second term is also computed from packed shares obtained from the online phase. And the last term is computed during the pre-processing phase. And this is a full presentation, and we have the full version of our paper available in the ePrint, and our open source benchmark is available through this link. Please do not hesitate to contact us if you have any questions on the SuperPack.